Hello, I am Joshua Flenley, candidate number 0190, and this is my video for the whitebox testing of my technical solution for my NEA. This video will be broken down into 4 sections based on the area of my checkers game that I am testing. This table shows the order that I will be conducting my tests, excluding the 5th section as there are no required whitebox tests for that area. For the first section, I will be testing the game logic and how the contents of my code is altered throughout the course of a checkers game. For the first test, I will be testing the select function within the game class. This will be to see if the piece is selected where the user clicks. To show this, I'll insert a print statement within the main game loop to show the row and column that the user clicks, as shown here, and I will insert a print statement into the game class here to show the row and column of the selected piece. So when I run my program and enter a game, if I select this piece here in row 0, 1, 2, 3, 4, 5, column 0, 1, 2, the coordinate where I click should be 5, 2, which as you can see down here it is. And then if I click on this piece here, you can see that this coordinate here is where I've just clicked to move my piece, but this is showing that the piece that was selected to move to this coordinate here was the same as this piece here, being in row 5, column 2. Then moving on, I will demonstrate this for the red piece as well to show that it's working correctly. So I will select piece in row 2, column 0, 1, 2, 3, 4, 5. So it should be 2, 5 instead. So when I click, selected coordinate is 2, 5, and when I click again, the selected coordinate is 2, 5, meaning that this test has been passed. For the second test, I will test that when a piece is selected, the valid moves are found using the find valid moves method and returned. I will test this by using print statements within the board class, and it will say the new location where you will be jumping to, and the intermediate jumps of the pieces that you'll be jumping over where applicable. So when I run the game and I select a piece, it should come up with, I should run the game first. I'm running the wrong file, my mistake. When I play the game and I select a piece, the valid moves should be outputted. So if I select this piece here, it's saying there are 2 possible moves that I can make. One in location 4, 1 as my endpoint, which is here, and one in 4, 3, which is here. And you can also see that neither of them are jumping over any pieces. So when I select this piece, it should let me jump over to this spot, which it has just let me do. So now for the red turn, I will show this again. So and if I click, it's showing that there's a new valid location to jump to at coordinate 3, 4 and 3, 6. So if I click here, it jumps to that location. And then to show that it recognizes a jump, when I click on this piece again here, you can see that there's a new valid location at 3, 2 and at 2, 5, but the valid location at 2, 5 jumps over the piece at 3, 4, meaning that the valid move includes this and should remove it from the board. So when I click on here, it takes the piece off the board, meaning that the second test has been passed. For test 1.3, the test will focus on the move function in board. I will show that when a valid move is selected, the board is updated with a new position for the piece, and any piece that has been taken from the board is removed. I have inserted three print statements within the game class to show that we have the piece's original coordinate, the coordinate that the piece is moving to, and for any coordinate that is in jump, uh, any pieces that are removed from the board. So when I start a game, if I select this piece here, you can see that when I select this valid move, it's the selected piece's coordinates is 5, 2, so 0, 1, 2, 3, 4, 5, 0, 1, 2, which is where the piece originally was. And the selected piece's new coordinates is 4, 3, which is here. When I do this for the reds, it does the same thing. It starts at 2, 5 and moves to 3, 4. And when I click here, you can see that the piece's new coordinates is 4, 3, which is, sorry, the original coordinates were 4, 3, which is where it was. The new coordinate is 2, 5, which is where it was now. And the removed piece was in coordinate 3, 4, and you can see that the piece that was at coordinate 3, 4 has been removed from the board, so this test has been passed. For all tests under 1.4, I will be evaluating the 16 moves draw method to verify that it correctly determines if there is a draw after a certain criteria are met. For test 1.4.1, I am checking that a draw is declared when there is one red king, two blue kings, and a blue man. To do this, I will insert a print statement here showing the number of red pieces, red kings, blue pieces, and blue kings at the start of the game, and here to show the number of red pieces, red kings, blue pieces, blue kings when the draw is declared to make sure that it is being declared for the correct reasons. So when I start a game and play 16 moves, a draw should be declared when in this state. I will play this game out and then come back after it is finished. When I move this piece here, it should declare the game as a draw for the fact that there is one red king against a man piece and two blue kings. And when I do this, you can see that at the start of the game there were two kings, a red king, and a blue man piece. And at the end of the game there are three blue pieces with two blue kings, meaning two kings and a man piece, and there's one red king, meaning that test 1.4.1 has been passed. For the next part of test 1.4, I am looking at the condition where there is one red king against three blue kings after at least 16 turns. This will be conducted in a similar fashion to the previous test, using the same outputs to verify the functionality. So when I start a game, you can see that the number of blue kings is 3, the number of red kings is 1, and we have one man piece here so that we don't have the 25 moves draw function be called. So I will play through this game and come back in a second. Now we're near the end of this test. When I click on this piece and jump over this piece here, the game should be declared as a draw, as it will be 3 blue kings versus a red king after 16 moves have been played. I click on it, the draw has been declared, and you can see that this is because there are 3 blue kings and 1 red king, which is the reasoning for a draw to be declared. So that means test 1.4.2 has been passed. Now for the final test on the blue pieces, I will verify that the game is drawn when there is one red king against one blue king and two blue men. This will be shown once again in the same way that I've shown the first two. where, as you can see in the program, it knows that there is one blue king, two blue men pieces, and one red king. So when I play through this game, after 16 moves, the game should be declared as a draw. I will do that quickly now. Once again, we're near the end of this game. So when I move this red king, it should declare the game as a draw, which it just has. And you can see that 3 blue pieces, 1 red piece, one of those blue pieces being a king and the red piece being a king, meaning that the conditions have been satisfied. So we can mark this test as a pass. Now for the final section of test 1.4, I will show that the previous 3 tests work for the red team too. So I will quickly change each of the 3 presets that I can have to have 3 red pieces and 1 blue piece. And then I will come back and show you the scenarios functioning. I have now updated the preset conditions to have three red pieces against the blue piece. So I'll now show you each of the conditions working again, but for the red pieces. So we'll start with 1.4.1 essentially, where we've got one blue piece, one blue king against 2 red kings and a red piece, which you can see again here is the case. So I will play through this game quickly. Once again, I'm near the end of the game, so if I move this piece, the game is drawn, and you can see that there is one blue piece, which is a king, against 2 red kings and a man piece. So the first part of test 1.4.4 has been passed. Now we will repeat this for the next scenario, which is 3 kings against a man. It's not a man, against another king. So you can see here we have 3 red kings, 1 blue king, and then an additional man piece to circumvent the 25 moves draw again. So I'll play through this game quickly. Now, if I move this piece over the red piece, it will draw the game. As you can see, it just has. And you can see that the reason that it's been drawn is because there are 3 red kings against 1 blue king, 3 red pieces, 1 blue piece, meaning that the second part of this test has been passed. And finally, I will test out the last circumstance where there is 1 blue king, 1 red king, and 2 blue man pieces, which you can also see here. So I'll play this game through quickly. As you can see here, if I move this red piece, the game should be drawn, and it has, because there is 1 blue king against 1 red king and 2 blue man pieces, meaning that the final part of this test has also been passed. So the entirety of test 1.4.4 has been passed, meaning that section 1.4 has all been passed as well, so the 16 moves draw function works as intended. Now moving on to test 1.5, I will show how the king's draw method verifies that there is 1 red king against 1 blue king, and that will cause a draw. To do this, I will output the number of pieces and kings at each turn to verify that when the condition is satisfied, green is returned from the relevant method by inserting a print statement within that if statement. So when I start a game with this current setup, you can see that when I make a move, the number of red kings, red men, blue kings, and blue men are outputted. And as you can see, there's 1 red king, 0 red men, as you can see on the board, 1 blue king, and 1 blue man, which you can see on the board as well. So if I take this piece off the board, it should declare a draw. And when I do, it has. You can see that there is 1 red king against 1 blue king as per these print statements, and you can say that a king draw has been declared, returning the value for green. So this test has been passed. For the penultimate test of section 1, I am going to test the repeated moves draw method. To do this, I will output the queue at the end of each turn to show how it changes leading up to the draw declaration. For each entry into the queue, there should be two Boolean values, one for whether a king was the piece that moved, and one for whether a jump was made. So if, for the last 25 moves, it's all king moves and no jumps, then the game should be drawn. As you can see here, if the repeated moves draw has been fulfilled, it will output the fact that a game has been declared as a draw because there are only king movements and 0 jumps in the last 25 moves, returning the value for green, and then it returns the value for green. And you can see that in the turn change method, we are going to be looking at the last 25 moves queue for each time the turn changes. So if I load into if I first set all kings as true, then load into a game and play through the 25 moves, we should see this happen. When I click on this piece and move it, you can see that for the first move, a king has moved and there has been no jump, and the rest of the values are none because there aren't 25 moves that have been played yet. So if I move this red piece now, you can see that the second move has also had the same outcome. And if I keep doing this, you can see that the queue is getting filled up after each move that I play. So we're nearly there now. So now when I move this piece and this piece after here, a draw should be declared. So when I click here, you can see that a draw has been declared, and that what's been outputted is the game has been declared a draw as there are only king movements and no jumps in the last 25 moves, returning the value green, meaning that this test has also been passed.
For the final test of this section, I'll be testing the turn change method, and I will be verifying that A changes the turn, B is called, and C updates the last 25 moves draw method. To show this, I will start a game and play a turn. And here you can see that we have called the turn change method. It's told us that we're changing turns. The current turn was the RGB value for blue, so it was blue's turn, and now it's switched to red, and the last 25 moves queue has been updated with false false, meaning that there are no king movements or jumps. I can do this for red. You can see that I'm switching from red to blue, and once again it's updated with false false, so there were no king movements or jumps. And finally, to show you that this is updating correctly, I've jumped over a piece, and you can see that we've switched from the blue turn to the red turn, and once again the last 25 moves draw queue has been updated. This time it's saying that there was no king movement and there was a jump.
And that concludes the first section of my white box testing. So I'll now move on to the second section, testing the functionality of the AI and its constituent procedures. This first test of the section is testing that the minimax algorithm returns a value when it is the red player's turn. For this, I will input a print statement to show the value that the algorithm has decided upon and the new board that links it to this value. So if I look at my code, you can see that I will be outputting as I said, the determined value of the board and also the new board. But if I enter a game and select an AI opponent, when I select a piece, wait for a second, you can see that once the AI has decided on a move to make, it's evaluated a score of 0, 0 for the best possible outcome it can get, and it's returned a new board object which will be different to the original one. So if I try that again for a different move, you can see now that the AI has decided on a move again. This time the evaluator score is 6,000, so it believes that it can find a beneficial board state, and once again it's returned a new board at a different memory address to the first one. So this test has been passed. Moving on, I'm going to test the possible valid moves method to verify that all the possible board states for all valid moves are calculated for a given color. To do this, I've inserted a print statement here within the maximizer section of the minimax algorithm to show all possible decisions that could be made for the given board state. So if I start a game and make a move, you can see that 7 decisions have been returned, as there are 7 possible moves that the AI can make. So there's one move here, another move here, this piece can move here, so that's 3. This piece can move here, so 4. Here 5, here 6, and then here 7. So there's 7 possible moves, and it has returned a different board value for each possible move. So if I were to play another turn, you can see it's moved again. This time the list is longer as there were more possible moves, and it's returned a different board state for each possible move played out. So this test has been passed. Now for test 2.3, I'll be testing the simulate move function to test whether a new move is simulated for each board state. I will use the easy mode on the AI for brevity, because if I use a higher search depth, the print statement will be called too many times and make the output confusing. For showing the functioning of this test, I will insert a snippet of code into the function that will output the updated board state after the move has been simulated, showing that a copy of the board is made and a move is tested on this board. You can see this inserted statement here. So I will unhash it now. So if I run a game, actually first of all I will hash the previous test out so that we don't see that as well. So if I run the game, we will see this in action, and here you can, if I copy this code snippet and paste it into our test text file, I'll remove the other boards so it's a bit easier to see. Here you can see an example of the board with a move that's been made of, so that an X represents a blank space, and a this this RGB value represents a red piece, and this RGB value represents a blue piece, as you'd be able to see in my constants file. Here you can see that this piece has been moved up here, and in response the board has simulated a move of this piece to move diagonally to here in response, meaning that this test has been passed. Now I will test the minimax function again, At this time, I will test that the algorithm makes a choice between two values, deciding on the more positive value on the maximizer's side and the more negative on the minimizer's. To show this, I will input a print statement into the function, showing the new value, the old value, and the value chosen as a result. As you can see here, I have an example on the minimizer's side where you have the new value, you have the old value, and you have the chosen value after it's evaluated between both of those. So if I run a game, here we can see the AI has made a move, and here on the maximizer side, the maximizer has two values to choose between. The new one, which is 7,000, negative 7,500, and the old one, which is negative 12,500. And after it has discerned the more positive one, it's decided that negative 7,500 is the best for that tree. And then if we look at the minimizers, it's choosing between the base value of infinity and the evaluated score that it's just found, which is minus 7,500, and the more negative of that is minus 7,500. So it chooses that, meaning that test 2.4 has been passed. Now I will test the alpha beta pruning of the minimax algorithm. To do this, I will run the minimax algorithm twice per turn, once with the pruning enabled and once without. If the pruning works, the time taken to move should be decreased by roughly half. So this shows what will be happening. So first I will run the minimax algorithm without alpha beta pruning and output the time it takes to find that. And then I will output the minimax algorithm with the alpha beta pruning and show the time it took to execute that. So if I start a game and enter a game against a hard AI, this will take a while as we're running this twice with the less efficient minimax algorithm as well. We will sit and wait for it to decide to make a move. Now you can see it's chosen a move, so we will look at the outputs, and here you can see that without alpha beta pruning, the minimax algorithm took 18.97 seconds to find a move, but with the alpha beta pruning it took only 3.7, showing that it vastly reduces the time it takes to find the best possible move. So that means the alpha beta pruning is working, and so test 2.5 can be marked down as having been passed. For the final test of the second section of this video, I will be testing that the function used to evaluate the board works as intended. For this, I am going to insert print statements into the checkboard method, that being a piece score, showing the difference in pieces that each team has, and multiplied by 1,000 to show its weight in the final score evaluation. There will be the king score, which shows the difference in number of kings that each team has, multiplied by 100 for the weighting. And then in get other scores within the board class, I will show the surrounding score, which denotes the number of pieces that surround each piece. So more positive for red pieces and more negative for blue pieces, multiplied by 250 for the weighting, as it's multiplied by 5 here, and 50 within the main section. Then there's the position score, which uses a weighted matrix to show advantageous piece positionings for each piece on the board, that having being more positive at the edges, as I am promoting a more defensive playstyle, with my minimax algorithm, trying not to lose as many pieces as possible. And then finally, there is the promotion score, which is how close a piece is to getting to being a king without being a king. So if a piece is in row 7, so row 6, for example, in the range 0 to 6 and is a red piece, it will have a higher score as it's close to being promoted to a king. Now to show this in action, I will start a game and enter a game against the medium difficulty AI. So I click here and the AI is moved, and you can see here that for this evaluated board here, we can see that the surrounding score is minus 12,500, as most of the pieces are still surrounded by, will still be surrounded by other red pieces and not very many blue pieces. We can see that the position score is minus 200, as the pieces are not in a particularly threatening position, or yes, not in a very threatening position. The promotion score is 0 because there are no pieces of the right color close to being promoted on the board, and the pieces score is 0 because there is an equal number of blue pieces as there are to red pieces. King score is 0 because there is an equal number of kings, that being 0 at the moment. And then to show this again, I will let this piece be taken. And now we can see that the surrounding score is still minus 12,500, but the promotion score is now 100, as the red piece is closer to getting promoted than it was before. Sorry, the position score is 100 as it's in a more favorable position. The promotion score is 0 because it isn't in the row before being promoted, it's in the row before that, so it's not very close to being promoted to a king. The pieces score is 1,000 because the red team has a greater number of pieces on the board than the blue, because the red piece just took a blue piece off the board, and the king score is 0 because there are still no kings on the board. So this test has been passed. This concludes the testing for the second section of the video. So moving on to the third section, I will focus on the testing of menus in the game. This section will be lighter than the previous two, as most of the transitions operate in a very similar manner. So first, I will be testing that the computer recognizes that a user has logged into the system and changes the appearance of the main menu accordingly. To do this, I will insert a print statement to show whether the user has logged in or not, then we'll output the name of the account button being displayed on the screen, as well as the username of the account that is displayed in the top right corner. Here you can see the print statements that I've inserted. So when logged in is not true, we will print whether logged in is true or not. We will print both of the account buttons that are being shown on the page at that point in time. And if logged in is true, we will print logged in now to show that logged in is true. We'll print the username that's currently being displayed in the top right hand of the screen, and the account button that's being displayed. The count plus equal 1 is to only show it once, as it will repeat it 60 times a second otherwise, as that is what I've set my frame rate as. So when I run the program and enter into the main menu, you can see here that logged in is false, and the two names of the buttons being shown on the page are login and sign up, which you can also see here. They are both login and sign up. So I will log into an account that I made earlier quickly to show the difference in the page after I've logged in. So here you can see that logged in is now true. The username is Joshua Flen, which is also shown in the top right hand of the screen, and account settings is the button which is shown on the page. So you can see that this is the case here as well. So test 3.1 has been passed. Moving on, I will be testing the checkers function to validate the game can be restarted when desired. To do this, I'm going to output the winner value of the game that has been played, then the restart variable to see whether the system recognizes whether a user wants to restart the game. Firstly, I am going to enter into a game, and I will play through the game to show the end screen once we get there. So I will come back once I've finished this game. Here you can see that I'm near the end of the game, and when I hop over this piece, the game has been declared as a blue win. So if I click restart, we can see that we're returning to the play menu. The game winner is our constant for blue, and restart equals true. So that means that part has worked. So I will re-enter the game and play through another game and show it in the opposite sense. Once again, I'm near the end of the game, so when I jump over this piece here, it declares the game as a blue win because the blues have won again. So if I click main menu this time instead of restart, it should say that restart is equal to false, and it just has. And you can see that we're back at the main menu, and that the game winner is the blue RGB value that we have. So this test has been passed. For the next test, I will verify that selecting the play button sends the user to the play menu, the quit to exit the program, and all other buttons and all other menus take the user to the desired menu logically. To show this, I have imported the Python logging library to create a log of each time a function is called for each menu, and each log will have the name of the function that the log is made in, as well as the message that is displayed alongside of it. For example, when I enter into the game, there will be a log for the main menu, and because the all of the code inside of main py is not within a class or a function, it will call it module instead. So to show this, let me start my program, and you can see here that from module we are entering main menu, which is also visible here. Now if I click login, you can see that I am told that I am entering the login menu and that I am within the login menu function, which means I'm in the right place. If I click back to main, you can see that the login menu recognizes that the back button is clicked, and the main menu has also been returned to, so it's told us that we are returning to the main menu. So if I log into an account, here you can see now that the login menu function has recognized that a user has been logged in, and we have been told that we are returning to the main menu, and you can see that we're in the code for the main menu. Now if I click on account settings, it tells us that I'm entering account settings, the account settings menu, as well as being told that I'm in the accounts main function, which is where the code for the accounts settings menu is homed. When I click change username, you can see that I've entered the change username function, and it's told me that I'm entering the change username menu. And if I click back, you can see that change username has recognized that the back button has been clicked, and accounts main has recognized that we're back there and has told us that we've returned to the account settings menu. I can do the same thing for the password. So where I click here, you can see that I've entered the password function, and it's told us that we've entered the menu. And I click back, the password change function has recognized that the back button has been clicked, and the accounts main function has realized that we've returned to the accounts settings menu. Now if I change my username from this, and is linked to this password, to this instead, you can see that the change username function has recognized that I've changed my username, and it has now returned me to the accounts main function. So I'm back on the main account settings page, which you can see is the case here. Now if I go to change password, I enter the username that I've just changed to, my current password, the desired new password, and a copy of the desired new password. Enter. You can see here that the change password function has recognized that I've changed my password, and the accounts main has realized that we've returned here, as you can see on here again. Now if I click sign out, you can see that the accounts main function has recognized that I'm signing out of my current account, and we have returned back to the main loop, and it's told us that we're returning to the main menu. Now when I click on sign up, you can see that we've once again re-entered the login menu function. That's because I used the login menu function to sign up to an account, log into account, and also to delete an account, as the login and sign up account pages are very similar. So now if I create a new account, the username will be account test, and the password will be test accounts. You can see that I have been told that I've entered the sign up menu, and that I am returning to the main menu after having my account be created. And so if I enter account settings and go to delete account, we can see that when I enter my username and I enter my password, we've been returned to the main menu on the screen. And you can see that I clicked the account delete button, and you can see that I've been told that I'm entering the delete account function. And then it enters the login menu function because I've used the login menu section for the account deleter as well. And then you can see that the user's been logged in, which means that the username and password were correct. And I've deleted the account as per what the account deleter function says. And after that, I've been returned to the main menu, and you can see that we are in the main menu code. Now I'll be testing the play game section. So if I click on the play game button, you can see that we have now moved into the play menu function and been told that we've been sent to said menu. If I click rules, you can see that play menu has realized that I've been sent to the rules, and you can see that now we are in the rules screen function. If I click the next button, you can see that the rules screen function has realized that I have clicked the next button and told me that I'm heading to the next rule screen. And this is the case as I click next all the way until I reach the end, which is indicated by the next button disappearing. This will also work for the previous button, as you can see here, because the rules screen function has told me that I'm heading to the previous rule screen. Now, if I click the back button in the top left hand of the corner, I should be sent back to the play menu, which is the case. And I'm told that play menu is the function that we are now in again, and it said back clicked, and we are returning to the play menu. If I click back to main on the play menu, you can see that play menu has realized that back has been clicked, and within the checkers function, we've been told that we have returned to the main menu, which is shown here on the board. Now, if I go into the one player section, you can see that within the play menu function, it has realized that we are entering the AI difficulty menu, which is also housed within the same function. If I click on easy, you can see that we have now moved into the checkers game function, and it has told us that we're entering the easy mode for the AI. If I go back to main, you can see that Checkers game has recognized that back has been clicked, and we are moved back into the checkers function, which is called when we enter the play game menu. I can do the same thing for medium, where we've now entered the checkers game function with the medium AI mode, and I can do the same for hard, where you can see I'm in the checkers game function entering the hard AI mode. Additionally, within the single player menu, there is also a back button, and if I click it, you can see that play menu has recognized that the back button has been clicked, and we have been returned to the main play menu. And the final section of the play menu part, if I click on 2-player, we can see that we have once again entered checkers game, and we have entered into a 2-player game. Now, for the next part of the test, I will be showing the end menu, so I will have to play through a game and come back and show you that after it is finished. As you can see, when I take this piece, the game has been declared as a win for the Blues. And if I show you the dialogue, you can see that we have now entered the end menu, and it's told us that we're entering the end menu function. If I click restart, you can see that we are once again within the play menu function and told that we are sent to the play menu. Now I will need to show you the end menu again, so I will play through another game. As you can see here, when I take this piece, I have reached the end menu, and if I click on the main menu button this time instead, we can see that we entered the end menu, and now we have returned to the main loop, and it's told us that we've returned to the main menu, so that has worked. And for the final part of this test, I'll be testing that the quit button is recognized. So if I click quit, you can see that the module, also known as the main loop, has recognized that we are quitting the program. So test number 3.3 has been passed. Now this ends the third section of testing, so I'll move on to the fourth and final section of this video, where I'll be testing functions related to database entries. For the first test, I will be testing the login function so that a valid username and password combination returns true, allowing the user to log in, and an invalid combination returns something else, not allowing them to log in. Here we can see the output statements that I have inserted to test this, the fact that this works. So when I run my program, if I log in, if I attempt to log into an invalid account, so say I'll give us a valid username but the wrong password, so check as you can say incorrect username or password, and here it outputs incorrect username or password, showing that it has been denied by the system. But if instead I put in a valid username and password, it says true, and you can see that we've been directed back to the main menu, and we have our username in the top right hand of the corner, so that means this test has been passed. Now for the final test, I'm going to test that the sign up function verifies that a new account has been created when a valid username and password is entered. Now to do this, I have inserted another statement into the code, but this one first, it uses the query users function that I created to test this, which is located in the db functions file. And what it does is it searches the users table within the checkers game database, and where there is a username, it will print the username, user ID, and also the hashed password to show that it's there. And if there is no username currently in the database, then it will return an empty string. So when I sign up to an account and I say I heart checkers is the username, and we're going to say hard AI 3 as our password, as that fulfills our boundaries set, or it doesn't. We'll enter 32 instead, as that will now work because it was too short. So if we now look at the output, we can see that first of all, when we tried to sign up, this was the first 2 times that I tried to sign up without it working, as I had an incorrect password. But here we can see that before the username was inputted into the database, there was nothing there. You can see that this has been printed out here before we've signed up, and the username was not in the database. But then after we've run the sign up function, we've used the query users function again, and this time it returns the user ID of 28, the username of iHeartCheckers, and the hashed version of the password hardai 32. So that means that this final test has been passed. Additionally, I have filled out the navigation table that I planned in the planning for my testing videos, and this shows all of the menus that you can go to from the other menus. For example, from the main menu, you can travel to the login, sign up, account settings, and play game menus, but nowhere else. Or from the account settings menu, you can navigate to the main menu, the change username menu, the change password menu, the account delete menu, and nowhere else. Now that I've finished this, this is the end of my testing video for the white box testing of my NEA. Thank you very much for watching.